Two people can stand in identical kitchens, follow the exact same recipe, and end up with entirely different dishes on the plate. Tiny variations in physical movement and temperature dictate the final texture of the egg protein. Today, we are removing the guesswork to engineer a light, uniformly golden, exceptionally spongy omelet. The required inputs for this experiment are simple: raw whole eggs, a pinch of salt, butter, a mixing bowl, a whisk, and metal frying pan. Mastering these chemical interactions makes a specific culinary outcome predictable and repeatable. Step 1 of the protocol starts in the bowl. Crack your eggs and add the salt right now, before any physical whisking begins. Raw egg whites are naturally ropey and prone to clumping because their proteins are tightly bound together. Salt neutralizes the electric charges within the egg proteins, causing them to uncoil and loosen up. This physical breakdown transforms that uneven, ropey texture into a smooth, uniform liquid. Eliminating that physical resistance early makes it significantly easier to blend the yolks and the whites together. This early application of salt serves as a structural tool, creating the foundation for a uniform, golden liquid base. The physical mixing phase depends on a specific window of aeration to achieve peak structural integrity. We are focusing specifically on the transition between collecting the egg in the bowl and applying the whisk. The mechanical purpose of whisking is to agitate the liquid, enclosing and retaining pockets of air within a developing protein matrix. At the 3-minute mark, the protein network reaches its peak stability. This duration allows for maximum air entrapment, while the protein matrix remains flexible enough to expand when heated. Continuing past this window causes the physical agitation to shred the protein network. Overbeating weakens the matrix until it can no longer hold the trapped gas. As the protein bonds break, the structure collapses into a flat, crumbly state. Terminating the whisking phase at exactly 3 minutes preserves that soft bite and prevents a dense, chewy failure. Now we move to the stove. Place your metal can over the heat and melt a pat of butter. We will avoid using cooking oil. The physics here are straightforward. Eggs consist mostly of water, and water and pure fats naturally repel one another. If you pour an egg into hot oil, the watery egg molecules forcefully push the oil away, thinning the barrier against the metal surface. This repulsion leaves a gap where the egg proteins form direct molecular bonds with the raw metal, causing the omelet to stick. Butter provides a solution through compounds like phospholipids and milk proteins. These compounds feature both hydrophilic and lipophilic parts, allowing them to anchor simultaneously to the watery egg and the fat in the pan. Butter acts as a molecular bridge, overriding the natural repulsion and maintaining a thick, impenetrable non-stick barrier. With the butter barrier established, pour the aerated egg into the pan and apply gentle heat for the final cooking phase. This thermal energy causes the tightly wound protein yarns to uncoil, a process called denaturation, and link together into a soft, 3-dimensional network known as coagulation. This delicate cage traps the water molecules within its gaps, keeping the food moist and tender. There is a strict temperature limit. Pushing the heat past 80 degrees Celsius forces the proteins to bond aggressively. Under high heat, the delicate protein net rapidly contracts and violently forces all the moisture out of the structure. This structural collapse, called syneresis, turns the egg into a dry, dehydrated protein sponge. Maintaining a low, controlled heat preserves the integrity of that water-trapping net, ensuring the final product remains fully hydrated and tender. To verify the results, we slide the cooked omelet directly from the pan onto a plate without using a spatula. The egg glides effortlessly, providing physical proof that the hydrophilic properties of the butter barrier functioned as intended. Now, let's cut the omelet open to visually confirm the structural achievements of this highly precise, temperature-sensitive process. Every technique is visible in the final result: the uniform color from pre-salting, the high volume from precise whisking, and glistening moisture from avoiding syneresis. A consistently perfect bite depends on controlling the specific physics and chemistry occurring inside the pan.